So we are going to see now how derivative affect the shape of the graph. So notice the following: if f prime x is greater than 0 on an interval I, then the function is increasing on that interval. If f prime x is less than 0 on that interval, then f is decreasing on an interval. So let's see by graph. So suppose you have a function. So in this case, function is from here to here, f prime x is greater than 0. So f prime x is greater than 0 here. Now from here to here, f prime x is less than 0. Then again, after this, f prime x is greater than 0. And you can see that f is increasing. You can see that f is decreasing. And here again, f is increasing. So derivative greater than 0 means the function is increasing. Derivative less than 0, the function is decreasing. What is the reason for that? There are many ways to look at the same thing. As you can see here, that the tangent lines have positive slope here and here as well. These two, in these two regions, tangent line has positive slope. From here onwards, and whereas here the tangent line has tangent line has negative slope. Now, if you want to see this algebraically, we can see the following. So f prime x is greater than 0 implies limit as h goes to 0, f of x plus h minus f of x over h. This is going to be greater than 0. That means for, let's take h to be positive, for some h positive, we have limit as h goes to 0, we have f of x plus h minus f of x over h is greater than 0. Now h is a positive, so this means f of x plus h minus f of x is greater than 0. So this means what? F of x plus h is bigger than f of x. So the idea is you have x here, you have x plus h. Because h is positive, it will be in the right of x. And then you can see that if you compare this value and x plus h value is bigger than that value. So you see the function is going to be increasing. Similar argument can be seen for function to be decreasing. So now let's see the following. Find intervals on the x-axis on which the function f of x, which is 3x to the 4 minus 4x cubed minus 12x squared plus 5, is decreasing and on which it's increasing. So the idea is, let's look at an example again. Let's draw a continuous function which is differentiable because this is a polynomial function. So if you look at a function, so from here to here, the function is increasing, but before it starts decreasing, the derivative has to become 0. Yeah. And then it starts decreasing, and before it starts increasing again, the derivative has to become 0. So when you're asked about an interval, you need endpoints of the interval. These endpoints of the interval are provided from the points where the derivative is 0 or derivative does not exist. So let's look at f prime x. So f prime x is going to be the solution. Let's look at f prime x. F prime x is 4. So 3 times 4 is 12x square cube minus 12x square minus 24x. And that can be written as 12x times x minus 2 times x minus x plus 1. And so f prime x equals to 0 would give us x equals to 0, 2, or x equals to minus 1. Now what we need to do is so these will give us the endpoints of the interval. So the intervals are how will you get the interval? We'll get intervals are minus infinity to minus 1, and then what is minus 1 to 2, and then the next interval is going to be, sorry, minus 1 to 0, then 0 to 2, and then 2 to infinity. So now what we want to do is we want to basically see what is the sign of the derivative, whether the derivative is positive or negative. So for that, we'll do what is called as the sine diagram. So sine diagram for f prime x. So what we do in the sine diagram is we draw a straight line like this, the real number line. We mark the points where the derivative became 0. The derivative became 0 at minus 1, 0, and 2. Now, what we have is the following. We will choose a point in this interval to determine what the sign is. And note that the sign of derivative will be either positive or negative, because to change the sign from positive to negative, it has to pass through becoming 0. Why? Because the function is the derivative itself is a continuous function. So let's choose a point here. So any point from minus infinity to 0, minus 1, excluding minus 1. So we have, let's take minus 2. Take minus 2. Minus 2, substitute in minus 12x, sorry, 12x times x minus 2 times x plus 1. So we have, let me write it again, 12x times x minus 2 times x plus 1. Now when I put x equals to minus 2, this will be negative. This part will be negative. And then this is also negative. So when you multiply 3 negatives, you get negative. So the sign here is going to be negative. That means the function is decreasing here. You don't need to find out the exact value. You just need to see what is the sign of derivative. Because we have already seen if the derivative is positive, the function is increasing. And if derivative is negative, the function is decreasing. So that's all we need to find out here for this part. Now let's take a point of our choice between minus 1 to 0, excluding the endpoints. So let's take a minus 0.5. When we take minus 0.5, we get, this is negative, but this guy is positive. So two negatives multiplied together give you positive. Similarly, let's take a point between 0 and 2. So if you look at point between 0 and 2, let's take 1. So if we take 1, substitute, 1 will make this positive. 1 minus 2 is negative. 1 plus 1 is positive. So 1 negative makes it negative. Similarly, let's look at the point after 2, say 3. 3 will keep this positive. So 3 will keep this positive, and this positive. So we get basically here to get positive. So the function is decreasing, increasing here, decreasing here, increasing here. So let me write that in words. So f is increasing on minus infinity to minus 1 union 2 to infinity, and f is decreasing on minus, so f is increased, sorry, my bad, f is decreasing on decreasing, or let's say f is increasing from where to where? Minus 1 to 0, right? Not minus infinity. Minus 1 to 0. And f is decreasing on minus infinity to, because that's where the sign is negative, union 0 to 2. So it's all decided by the sign diagram. Another quick way to do this was, notice that you have roots of multiplicity 1. So once you decide what is the sign here, then the signs are going to alternate. Now, this derivative also helps us to decide whether the function is increasing or decreasing. Sorry, function has a local maxima or local minima. So let's see. So suppose we have f prime changes the sign. So we are at c, Suppose f prime changes sign from positive to negative. So f prime is positive before c. That means the function is increasing. After c, the f prime is negative. That means it stops decreasing. So in this case, we get what? So this is increasing, this is decreasing. In this case, we get local maximum. So if f prime changes sign from positive to negative, f has local maximum at c. Similarly, if f prime changes sign from negative, that means before c it was negative, that derivative was negative, that means the function was decreasing. After c, the function started increasing. So in that case, we get what? F of c is local minimum. Now it can happen, for example, f of x equals to x cubed. Let's look at this graph. In this case, you'll see that the sign, so what is the, where does the derivative become 0? F prime x equals to 0. This gives us what? This gives us 3x squared equals to 0, which means x equals to 0. So when you draw the sign diagram, now since the derivative is 3x squared, it's positive here, it's positive here. So if the derivative does not change its sign, you will get neither local maximum nor local minimum at C. So that helps us now to solve the following problem. So we have find all the local extrema of this function, f of x equals to this. So now we have already done the computation. So I'm going to recycle that computation from this problem here, example 3. So f prime x equals to 12x times x minus 2 times x plus 1. And we had sign diagram. Now sign diagram for what? Sign diagram for f prime x. Yeah. So sign diagram for a function means you're just checking where the function is positive or negative. So sign diagram for derivative is where you're checking where the derivative is positive or negative. So you mark these points again, minus 1, 0, 2. So first step is to find, step 1, find critical points or critical numbers. That is C such that f prime C equals to 0 or f prime C does not exist, where C belongs to the domain of the function. Note that critical numbers are the only numbers which can be local maximum or local minimum, and at those points the critical numbers come from the domain of the function, and at those points derivative is either 0 or does not exist. So we have negative here, as we saw earlier, positive, negative, positive. So in this case, what happens is the sign changes from, if it's negative, means it goes negative, and then after that it changes to positive. So this means f of minus 1 is local minimum. And this test is called first derivative test because you're looking at the sign of the first derivative, right? You're looking at first derivative. So therefore, this is called first derivative test. So f of -1 is local minimum. Similarly, f of 0, sign changes from positive to negative. So positive means the function was increasing, after that decreasing. So f of 0 is local maximum. Now comes the third critical point. So critical points are critical numbers here are 0, 2, -1. So now what about f of 2? So let's see, at f of 2, before 2 the function was decreasing, after 2 the function was increasing, or the sign of the derivative changed from negative to positive. So you don't need to memorize it. When you draw it, you can clearly see that f of 2 is local minimum. But however, we need to find out these values. So let's substitute f of 0, f of -1. What is f of -1? So if you put -1, you get 3, -4, -12. So 3 -4 -12 is 3 minus, sorry, f of, so it will be 3 plus 4 minus 12 plus 5. So 3 plus 4 minus 12 plus 5. So 3 plus 4, so this is going to be 0. F of 0 is 5 and f of 2 is -27. So this is a profiling of local maximum local. Now let's look at the next example again. So what is f of x was absolute value of x is x if x is greater than or equal to 0 and minus x if x is less than 0. And this gives us f prime x is 1 if x is greater than 0, -1 if x is less than 0. Now what about at 0? At 0, not defined at 0 because undefined at 0 because of a corner, right? So this means x equals to 0 because 0 does belongs to the domain of function. Since f prime 0 does not exist and 0 does belongs to the domain of function. Note that critical number should come from the domain of the function. Now what about Sine diagram? So Sine diagram for f prime x. So at 0 it's not defined, but we have before 0 it's -1 here and after 0 it's 1, so it's positive. So therefore f of 0, which is 0, is local what? Let's check it out. Before 0 it was decreasing, after 0 it starts increasing. So f of 0 is a local minimum. So now our goal is to understand how is the shape of the graph. So note the following. In this case, here also the function is increasing, and here as well the function is increasing. Yeah. But if you notice in this case, the first case, the function, the derivative, the slope, or sorry, the tangent line lies below the curve. In this case, the tangent line lies above the curve, right? So we should be able to distinguish between these two shapes because after all, we are determining how derivative decides the shape of the function. Now note that first derivative in both the cases is positive. Why? Because the function is increasing. So function is increasing, the first derivative is positive. So how do we determine which of the cases, how will we be able to capture this scenario? So notice the following. So first, let's look at the following graph. So in this case, we have that the tangent line lies below the curve. So such a shape is called concave up. So what is a concave up? So if the graph lies above all the tangent lines on the interval, then we say that graph is concave up on interval I. So this is my interval I. You can see that the graph is concave up. Now we want to understand how to capture that scenario. So let's see what can derivative really capture this. So we already saw that derivative cannot distinguish between these two guys, right? But notice the following. So let's take this point here. Now, here at this point, the slope of the tangent line is the slope of the tangent line is the slope of the tangent line here is 0. So let's just draw this correspondingly. That means the slope of the tangent line. So if I'm going to draw from f of x, I'm going to draw f prime x and see what do we get. So here the derivative is 0. Now before that, the tangent lines have negative slope. They have negative slope, but it's going to become 0. So before this point, let me draw it properly. Before this point here, the tangent lines have negative slope. So at this time point, the slope of the tangent line is 0. But before that, the tangent line has negative slope. And after that, the slope starts basically what is positive and starts increasing. So this is how roughly the graph of f prime x may look like. So that means f prime x is an increasing function. And for every increasing function, if you take derivative of that, that's going to be greater than 0. That is same as saying f double prime x is greater than 0. So so we say that if the second derivative is greater than 0, then the graph is concave upward. Similarly, if you look at the other case, if what in this scenario, the function is concave downward, and you can check that the second derivative is less than 0. Okay, so rule of thumb, f double prime x is greater than 0 on I, f is concave upward, smiley face. F double prime x is less than 0 on I, f is concave downward. Yeah, frowny face. Now notice the following. For some graphs, you'll see that the function is concave upward and then it becomes concave down. So at this point, the function was concave up from here to here. But after that, the function becomes concave down. Yeah. So this point becomes special point. This point P on the graph, this point is called inflection point. Similarly, not only that, if the graph changes from concave, so here it's concave down to concave up, even if it changes from concave up to concave down, then we get what is called as inflection point. So here the second derivative is greater than 0, here the second derivative is less than 0. Now if your function is continuous enough, and if you take the second derivative, as well, and that's continuous. What will happen is before it changes from less than 0 to greater than 0, the derivative should be, second derivative should be 0. Or in this case, if you look at 1 over x, the function second derivative of f of x is, first derivative is minus 1 by x squared, second derivative is 2 by x cubed. So you see here, the function is concave up here and it's concave down here. It's concave down here. But before it changes from concave down to concave up, it has, second derivative has to pass through the point where the second derivative does not exist. Okay. So we'll come to how to find out the point of inflection in a minute. Okay. So there is one good side effect of this. So namely, we get a second derivative test to check local maximum and local minimum. So if we look at f of x equals to, say, f of x equals to x to the power 4, or let's take x squared. The second derivative, so the graph looks like this. So if the first derivative is 0, that means you're here. And if the second derivative is greater than 0, so that will happen when the graph is what? Concave up. So we get this shape here, right? So not only you have a critical point, but the function is concave up around that critical point. In that case, we get what? F has local minimum at C. Similar thing, we'll get F has local maximum at C. If first of all, what should happen? F prime C is equal to 0. That means it's a critical point number. And not only that, second derivative has to be less than 0. That means the graph has to be concave down for it to have a local maximum. However, if f prime C equals to 0 and f double prime C is also 0, then the test fails. An example of that would be f of x equals to x to the 4, f of x equals to x to the 5. Yeah, so if you look at x to the 4, x to the 4 and say minus x to the 4. So x to the 4 graph looks like this, like x squared, but slightly more flatter, around 0. Now here we have, in this case, let me call this as g. Now f prime x equals to 0 at x equals to 0, and f double prime x at 0 is 0, right? But what happens here? But f has local minimum. Similarly, let's look at g of x. So g prime 0 equals to 0, and g prime doubles of second derivative 0 is also 0, but g has local maximum at 0. Like say for example here. So this is how x to the 4 minus x to the 4 will look like. Reflection in x-axis. So we get here, so second derivative equals to 0, the test fails. So the test basically fails, or fails is same as inconclusive. So let's sketch the graph of the following function. So we have f of x equals to 3x to the 4 minus 4x cubed minus 12x squared plus 5. So what are the steps in graphing this function? So first of all, we'll find the critical number. So f prime x is 12x cubed minus 12x squared minus 12x, so 24x. And we have already seen this in the upper part. That is 12x times x plus 1, x minus 2. So critical points are, critical numbers are 0, minus 1, 2. Then I'm going to draw the sine diagram from before. So sine diagram for f prime x. So again, we have already done this computation, so I'm just gonna write it down. We have minus 1, we got 0, and we got 2. We also had minus plus minus plus sign. So the function is decreasing, increasing, decreasing, increasing. And we have f of minus 1, which was 0, is local max. F of 0, which was 5, was local min. So f of minus 1 was local minimum, right? Because the sign is changing from negative to positive, right? So it's going to be local min. F of 0 is local maximum, and f of 2 is local minimum. And not only that, we found out what these values were. So this value was equal to 0, this was 5, and this was minus 27. Now we have seen the sine diagram for f prime. Now we need to look at the second derivative to see whether it's concave up or concave down. So sine diagram for the sine diagram for f double prime of x. So for that, we have to look at the following. So take second derivative of x equated to 0 or does not exist. But in case of polynomials, the derivative always exists. So we'll just equate it to 0. So we get what f double prime x equals to 0 implies. What is the second derivative of this? This will give me the second derivative is 3x squared minus 2x minus 2, and that can be seen as 3. We need to solve this, but you see that there is no root which can be done by splitting the middle term. So you'll have to use quadratic formula. So the roots are equals to 0 when x equals to minus 1 plus or minus root 7 over the whole divided by 3. So now we need to basically look at the sine diagram for f double prime. So concavity, so sine diagram for f double prime. So how does that go? You basically draw a straight line like this. You mark where the second derivative becomes 0 or does not exist. Yeah, that's important. Here in this case, we do not have a case of does not exist. So we have minus 1 minus root 7 by 3 minus 1 plus root 7 by 3. Now let's check a point before. So before this point, let's check sufficiently large. So let's see, minus 1 minus root 7. So that is going to be around, say, minus, even if it is around minus 9, I can take a 4 here to check what is happening. So if I take a 4 and I substitute in this equation, you will see that this equation can be written as, here it will have a positive sign. Here when you put 0, you will get -2, so negative sign. And here you'll have positive sign. So F is concave down, sorry, positive sign, so F is concave up, concave down, concave up. So for F, concavity. Now we have all the information to sketch the graph. With this, we are able to now draw the graph of the function. So first we will we need to draw a bit further down. So the way it is, first we need to find out the points which are critical points. So the critical points are 0, -1, 2. So -1 to -1, 0, and 2. So let's see, what is the value at -1? So we need to scale down the graph. So we'll go 5, 1, 5, 10, -5, -10, -15, -20, -20, -25, -30. The reason for that is because the local minimum, f of 2 is local minimum is -27. So f of 2 is -27. So f of 2 is -27. So that point is going to be somewhere here. So somewhere. Now, what are the other pieces of information we have? We have local 0 is local, f of 0 is 5 is local maximum. So 5 is local maximum. Now f of 1 is, f of -1 is also local minimum. Now f of minus 1.22, the function value is 0. So it's just slightly, so it's here, -1.22. This is the inflection point, so it's just here. And similarly, f of 5.4, which is half of here, also the function value is 1. So these are the inflection points. So let's see. So before 1 minus √7/3. Before this, the function is what? Concave up. So before that, the function is concave up, and it is decreasing all the way until -1. Yeah. So it's decreasing all the way until -1, but it's concave up. Before this, the function is basically concave up. So it's decreasing. After that, the function basically, after 0, the function starts decreasing all the way until what point? So it starts decreasing, but we should mark the inflection point now. So at 1.25, so at 1, so we'll have local minimum at 2, which is 2 point, this is our local minimum. So our local minimum is at 2, and the function basically goes down. So local minimum is at 2. It will cross x-axis at some point, but before that, it becomes concave. Now the concavity changes again at 1.1251, where it becomes what? Again, from concave down, it becomes concave up. So it goes down quite steeply at 1 to become 13. So quite steeply, so that 1 it becomes 13, and from concave down, so this is concave down, now it changes concave up to basically go to first, go to the local minimum, and then it keeps on going, basically local minimum. After that also it's concave, after that also it's concave up, and it is what? It is increasing after 2. So it's increasing after 2. So this is how the graph looks like.